Thank you. I'm Gangotree Chakma from University of Tennessee. Today I'm going to present a talk on behalf of Katie Schumann. She's from Oak Ridge National Laboratory. She couldn't make it this year, but she said hi to you all. So this work is actually in collaboration with Oak Ridge National Lab and 10 Lab from University of Tennessee. But what I'm going to present today is mostly Katie's work, but I try my best to provide as much information I can on this work. So let's get started. The topic I'm going to talk about today is training neuromorphic systems for scientific applications. Before I dive to the training algorithms, I'd like to define what do we mean by spiking recurrent neural networks. So there are some key elements that we consider that needs to be defined while we are looking for a neural network. So when we look at a neural network, we try to find what's the topology of the network. That means how many neurons are there and how the neurons are connected, which refers to the level of connectivity. And we also try to look for if there is any feedback connections between the neurons of one layer to the other, which refer to the recurrent connections present or not. And then the one most important things to notice is that we consider the parameters of network. And I think we have mentioned 3 of the most important parameters here. Those are the weight of our synapses, thresholds of our neurons, and the delays of one connection to the other. Now let's take a look at some possible training algorithms that we have considered for this work. We have some performance matrices that we try to put so that we can compare different algorithms in our studies. So those are the topology. Is the topology defined or trained? How are the delays, and are the delays defined or utilized? And what's the weight? What is the training time for each algorithm? And most importantly, how broad the algorithm can be applicable in various applications. So we have considered 4 training algorithms. These are backpropagation, spike time dependent plasticity, or STDP in short. And the rest of the 2 are evolutionary approaches and liquid state machines. Let's start with backpropagation. So as you can see on the table, it clearly defines the weight values of the network. The topology is restricted in a sense that there is usually some sort of layer structure, and there are some restrictions on what the recurrent neural networks would look like, or how many layers would there be in the network topology. The training time is moderate, and it can be applicable for a broad application regime. Then comes STDP. For some algorithms, the STDP has defined the topology such as winner-take-all topology. And you can see the delays are utilized here, but they are not defined. The weights are defined. The training time is also medium. But for me, I believe that STDP is going to be one of the promising algorithms in very near future. But right now, we do not have any clear idea how broadly we can utilize STDP for a wide variety of application. Now let's talk about the last 2, which are evolutionary approaches and the liquid state machines. Clearly, they are both advantageous than the other 2. You can see the topology is defined. The weights are either random or defined. The delays are defined. The training time for evolutionary approach is really slow. So that's the key disadvantage for that approach. Because here the convergence is slow, it takes a lot of time to simulate to get a perfect network for some specific application. But the good point for evolutionary optimization here is you can apply it to a broad range of application, including classification tasks, anomaly detection, and some control application. So for the rest of the presentation, I'll be focusing on the last 2 approaches, which is evolutionary optimization and liquid state machine. Now we know the possible algorithms for our training. So let's talk about how this neuromorphic system we are trying to correlate with spiking recurrent neural network. We all know that the neuromorphic system, it supports spiking networks along with variable delays and programmable connections. But if we want to utilize the topology fully, we have to utilize the programmable weights, delays, and the recurrent topology. In this work, we are trying to consider smaller networks in a sense that if we use smaller networks, the activity will be less, and that less activity will refer to less energy and power usage. And moreover, if we consider any given application, the one thing we have to consider is that how adaptive that application is to our algorithm is. Because there are some algorithms that are very inflexible for some non-classification tasks. So for that reason, we have utilized a simple spiking neural network architecture. We call it Neuro-Inspired Dynamic Adaptive Architecture, or NIDA in short. It's the PhD dissertation of Katie Schumann itself. So it's a very simple spiking neural network embedded in 3D space. It uses integrate and fire neuron, and also it has delays with programmable delays and weights. It's flexible in structure. It has a very general topology. Any neuron can be connected to any other neuron using the synaptic weights. So as you can see on the left picture, there are input neurons, output neurons, and some hidden neurons. It's a very sparse and small network connected with some inhibitory and excitatory synapse. So on the right, that's just the NIDA approach, how the charge event is propagated from one layer to the other. So it's the change in charge event comes to the neuron, and the neuron accumulates the charge, and whenever it reaches a certain threshold, it fires. So when it fires, it also clears out itself. That means it gets ready for the next event. So that's how NIDA tells us the charge is passed from one connection to the other. So we have the neural network architecture for our spiking neural network algorithm. Now we want to implement it on the hardware. That's why we have developed two implementation. One is fully digital, and the other one is a mixed signal memory-steep neuromorphic architecture. So that's the one. I have a poster over there. So it's mixed signal in nature. It has memory-steep synapses because it's nanoscale, non-volatile, and it has low energy consumption. And for the neuron, we have mixed signaled CMOS neuron. So on the top picture, those green boxes, squares, those are our memory-steep neuromorphic core. So if we enlarge it, we have several synapses and one integrate and fire neuron for each of those cores. So on the bottom one, that's the layout of our taped out chip. On the right side of the chip, that's our memory-steep neuromorphic core. On the left side, that's the DANA, or the fully digital core. So it has been done in collaboration with CNSC, SUNY Polytechnic, Albany, New York. They have an in-house fab where they fabricate CMOS with memristors. So we got the advantage of that, and we have just taped it out 6 months back, and we are trying to get it back by March, hopefully. Okay, now we know about our hardware, our neuromorphic architecture, our neural network architecture. Let's take a high-level view, and let's talk about how we are training our neuromorphic system. So we have developed our own evolutionary optimization framework. We call it evolutionary optimization for neuromorphic system, or EONS. It defines the topology and parameters of the network. It works like a typical genetic algorithm in which an initial random population is initialized using some randomly initializing potential solutions. After that, the networks are evaluated and ranked from the best to the worst. And then some selection some selection process is gone through so that we can sort out the best networks to work as parents for our next generation or children. And then the parents are our parents generate the child population through mutation and crossover selections. So this evaluation, selection, reproduction, this whole cycle is run again and again. Once we reach to a certain selected network, accuracy of network, then we stop it and we call it, okay, we have got the perfect network for this specific application to run. And this is the network we get is usually very small, sparse, so that we can get less energy and area. To finish this slide, we can say that EONS has been applied to 3 of these neuromorphic architectures that I've been talking about: the NIDA and the digital implementation and the mixed signal implementation. Okay, for this work, we have also considered reservoir computing approach. Here we have utilized a randomly initialized spiking recurrent neural network as the liquid, and we have trained a fully connected readout layer, and it has backpropagation advantage so that it can get the output values for the reservoir. Now, I'm going to talk about what's the scientific application that we are considering so that we can use this framework. So the application that we looked at here, it's a temporal scientific data classification task on the data from Fermi National Accelerator Lab. So if you can take a look, that we have collaborated with high energy physicists. But just a disclaimer that all you can see on the slide is all I know about the data itself. I have no idea how they're getting the data, they're analyzing it. We just get the data from them, and we put it on our network and simulate it. That's all I know. But here, the key thing to note here is that it's a neutrino scattering experiment. So the whole detector is exposed to the neutrino beam, which is so you can see the green projector. That's where the neutrino beam goes through to that grayish cylindrical thing. So that it's kind of like a classification of a horizontal region. So all those tubes you can see, that they have actually 11 levels, 11 regions to take the data out from itself, and then we get it for our classification task. So that's the application. Now I'm going to talk about the data input types. So we have 2 data input types. One is the energy lattice in the top, and then the bottom one is the time lattice. Both of these 2 data types have 3 views. One is X view, that when you look at directly down to the detector, and one is U, and the other one is V. Those are actually angled view from the detector. For this presentation, I'm actually going to concentrate on X views only, because we have the data of X views here. The energy lattice, we use it for the deep learning approach, and the time lattice, we use it for the spiking recurrent neural network approach. The energy lattice tells us the average energy for a certain span of time, and whenever so you can see all those the dark blue, there is no energy over there. But when you see that red and the yellow one, that means it has hit the threshold energy on that particular pixels. So for the deep learning, we are considering all the data itself by pixels. And then again, for the spiking neural network, the time lattice, it tells us at what time the certain amount of energy is higher than the threshold. So the highlighted one, those are the time when it got higher than the threshold. So as you can see, though it looks, both the lattice time and the energy lattice, they look pretty much same, but they are different. They tell us different information. But the thing to notice here is that all of these 6 views, they are the picture of a certain, like only one instance of time, but from different views and with different information. Okay, we have got the data inputs, we have got the application. Now I'm going to show the results that we have got from our simulation for both deep learning approach and spiking recurrent neural network. The best results we obtained for our X view are both very comparable, as you can see, because for the convolutional neural network result, we got it like around 80.42%, whereas the spiking neural network, we got it 80.63. So it's really comparable. But the interesting thing to note here is that if you look at the size of the network, those are radically different. The upper one, we have like 127 by 50. That's actually the data input size. So what we did for both the approach is we got 50 input neurons, and we led those neurons to fire for 127 different times so that we can get the 127 by 50 whole matrix. And then for the convolutional approach, you can see there are some pooling network, and then on the last, those are the fully connected networks that has 196 neurons in layer 1, 98 neurons in layer 2, and the output is there are 11 neurons. But for spiking neural network, there are only 90 neurons and 86 synapses. So that's a pretty big difference from the deep learning and the spiking neural network approach. We have also tried to get the energy estimation using our memory-strip DNA architecture that is around 1.66 microjoule. Then the interesting thing to note here is that about the EONS system or the EONS framework. This is a genetic algorithm, so it's very slow in convergence. So you can see if we use just 100 computer nodes for an hour, we can reach up to 70%, which is very slower than the 80% we got. But EONS is really scalable and parallelizable. So if you put all the 10,000 computer nodes or use the Titan supercomputer in Oak Ridge Lab, we can reach up to 79%, which is really close to the one we got it initially, just within an hour. So if you want any network and you are in a hurry to simulate, so what you need to do is just pull up all your resources using spiking neural network, and you'll reach very high efficiency with smaller size network. Another thing to note here is if you look at the actual versus the guessed labels, for our classification task that you remember, there are 11 region or labels. You can see that there are 5 labels that have not been recognized very perfectly. Those are 0, 4, 6, 7, and 9. So on the right, you can see all those 5 labels, they have very few instances. So EONS is not able to label those perfectly every time it gets those instances. So that's a drawback. What can we do to mitigate this? So what we did is we want to get perfect results. We introduced a punishment layer for the fitness or the objective function for this EONS system. What it did is like whenever it cannot recognize the label itself perfectly, it gives punishment, or it reduces the synaptic weights or something. And then after that, we get a network which is big, that is 140 neurons and 355 synapses. I mean, it's bigger than the other one I had in 90 neurons and 86 synapses. But the good point is we are trying to increase the accuracy by 3%. So it's increasing from 80 to 83 and 86 for both training and testing. So that's an advantage using EONS, where you can easily update your fitness function to get a perfect or accurate result, mostly perfect result. As I said, we have also considered reservoir computing. So we did the same things. The inputs are same, 127 by 50 inputs, having 50 input neurons and 11 output neurons. We encoded the input in the same way like we did for the EONS-trained spiking neural network architecture. So this was a very random topology, very different. We got a very smaller network. And we also got it, as you can see, the testing accuracy and test accuracy, those are higher. But the test accuracy and the training accuracy, it's 95 and 81, so it's a very big difference. That means we most likely will be in danger of overfitting. But I think I'm hopeful with that. If we try to simulate or generate some network with some smaller networks for reservoir computing only by itself, I think we can mitigate this problem in future. Okay. This slide actually is my favorite one because all I've been talking about is everything is there here. So we're trying to compare 3 different methods. One is the convolutional neural network. Another one is spiking neural network trained with EONS. And the third one is liquid state machines with spiking liquid. So we are trying to compare based on training accuracy, the network size, and the approximate training time. So if you take a look at the table, you can say that the network trained with EONS is better because it has higher testing accuracy. It has a lower network size, but the only disadvantage is it has a larger training time. But however, in many cases, if you try to consider the cost of training worth to getting a smaller network size for smaller energy estimate, I think we can go for the spiking neural network trained with EONS. And if you are trying to get as I said, if you're trying to get a network very fast enough, very small, and with smaller training time, I think liquid state machine network, that will be a very good approach to get that. Before I wrap up, these are some key points that I'd like all of you to take home. Firstly, we achieved the best of performance with spiking neural network using evolutionary optimization. But I think liquid state machine is also very promising for near future application. We have also produced some comparable results for 3 approaches. But we all have to admit that there is always a trade-off between the resulting network size and the training time we will have. Then backpropagation and liquid state machines may be able to be trained faster if we use less resources, but the resulting networks will be larger or bigger. That's why we tend to use EONS so that we can get smaller networks which will give us less activity and which will give us smaller footprint to get small energy. Lastly, I'd like to thank all of my collaborators from UT, ORNL, and Gabe Pardue from Fermilab. He's the one who gave our insight to the data and who supplied the data. And Department of Energy and Air Force Laboratory for funding us. Thank you very much.
Very much. There's a question.
Yeah, so thank you for an interesting talk. In computer science, we have a notion of an anytime approximation algorithm. That means the more time you let the algorithm compute, the better your solution can be. Does your results suggest that something comparable can be with spiking networks? The more energy you allow the network to use, the better your accuracy can be.
For this work, I think the results I have shown is for the liquid state machine one, it was run only in our laptop. But the one for the spiking neural network with smaller 100 nodes, that was in the laptop, but the 10,001, that was in the Titan supercomputer that we ran. So we were trying to think how we can optimize the energy so that we can use less resources. I mean, we don't have to rely on the supercomputer always. So we wanted to see how there are some other algorithms that we can try to improve so that we get less resources, but with better efficiency. Thank you.
Can I ask you a question on the reconstruction of tracks in the particle physics experiment? Of course, there is a lot of standard software algorithm available that people have used traditionally. Can you compare your neural network results with the traditional approaches in terms of precision and also the computational needs?
I think that would be better question.
People have solved that problem for decades, reconstructing tracks and these detectors, and they have been very successful. And it will be interesting to see how the neural network approach really compares to this traditional
Sure.
method. If you don't know.
I don't know because it's all Katie's work,
Okay,
so
okay, that's
she'd be the best person to ask.
Okay, okay.
Thank you.
Are there other